In this video, we're going to discuss graphing and linear relationships, including slope and the y-intercept. We're going to talk about graphing and linear relationships because graphing data to find relationships is an extremely important skill that you need to have moving forward in any math or science field or course that you wish to take. So we're going to start by looking at the Cartesian coordinate system. The Cartesian coordinate system is a set of, in this case, two axes, the x-axis and the y-axis. These axes and the values on these axes, meaning specifically the number of lines over you are from the center point called the origin, give you a location, a very specific location, for any spot that you can think of. For example, since the origin is located at point 0, 0, if you were to move to the right 1, 2, 3 lines and up 2 to this point right here, you would be located at the point 3, 2. Okay? The first number, 3, is the x-coordinate. It tells you how far to the right or left to go. Positive values are to the right, negative values are to the left. The second number, the 2, is the y-coordinate, meaning this thing right here is called an x-y pair. The y-coordinate tells you how far up to go, or down. Positive values are up, negative values are down. The Cartesian coordinate system is made up of 4 quadrants. Quadrant 1 is located right here, and this is where we are chiefly going to spend our time today. Quadrant 2 is this one. Quadrant 3 is this guy down here. And this one is quadrant 4. Again, we're going to spend most of our time in quadrant 1 dealing with positive x values and positive y values. So let's take a little bit closer look at the first quadrant. Here's the first quadrant. Now you can see that we are focused only on the first quadrant, sort of the upper right part of the Cartesian coordinate system. Now, as I stated before, this is the y-axis and this is the x-axis. But we're not always going to be plotting x's and y's. Our x's and y's are actually going to be variables or things that we are changing and assigning numbers to and talking about, and actually looking for a relationship between. So when we talk about the x and y axis, we're actually going to be assigning a variable to that axis so that we can put the numbers that we get when we collect our data in the appropriate place. So a way that we're going to do this and a way to help you remember this is the acronym dry mix. D-R-Y-M-I-X. Now, dry mix. I'm going to start with the mix part because that's generally where you want to start. The M in the mix stands for the word manipulated. Now, the manipulated variable is the one that you're controlling, the one that you are changing, the one that you are manipulating. And the one that you're manipulating is considered to be called the independent. Oops. Little spelling error there. The independent variable. And the independent variable always goes on the x-axis. So this axis down here is considered to be the independent axis. And whatever your independent variable is, you're going to list it there and you're going to record its numbers down there. Now, the other part of the acronym, dry, the D stands for the dependent variable. The dependent variable is the one that responds to the changes that you make to the independent or manipulated data. So when you change the independent variable, there should be a corresponding, if there's a relationship, change to the dependent variable. And the dependent variable goes on the y-axis, which means that this axis over here, the y-axis, is where we're going to put our dependent variable. So I think it would help if we actually were looking at some data and looking at an example of this to help us sort of see what happens and see how this works. So if we we can see some data for tree growth over time. What you can consider for this data is that someone planted a tree in their yard, and then they checked how tall it was every year or every few years and recorded the data. So what we need to first do is we need to assign our variables. Our variables are right here. Our variables are time and height, and their units are in parentheses just below them, years and feet. So what we need to do is we need to determine which of these is the dependent variable and which of these is the independent variable. So again, we stated that the independent variable is the one that we are manipulating. Now, we're not really changing any of these, but what largely happens is that time is going to act as our independent variable. You can consider that as time moves forward, the height of the tree will change. So we're going to go ahead and state that time would be our independent variable. We're going to record it down here below the x-axis, and we're going to put its units in parentheses right next to it. And that means that when we assign numbers using a scale down here for our graph, those numbers will represent different times or different numbers of years that we've allowed the tree to grow. That means that height would be our dependent variable. We're going to record that right over here on the y-axis of the graph. We're going to make sure to put its units in parentheses right there with it on the y-axis. And again, we would then assign a scale, and the numbers that we use on this will represent the height of the tree at any specific time that we're talking about. So let's go ahead and actually plot the data. So let's come on over here. With the same general setup, we have an x and y axis. I did switch over here so that we have the grid. We actually have the graph paper there for us. And so before I actually go ahead and plot the data, what I'd like to do is I'd like to touch base on the scale. So the scale of your graph is assigning a value to each box. Okay, so you can see down here on the time axis, the first line here is 0. Okay, let's do this. Okay, right over here we have 0. Okay, and you'll notice that there are 1, 2, 3, 4 lines before I actually mark off the value 1 year. So that means that each line in itself is 0.25 or 1/4 of a year. So then you can see from 1 year to 2 years is another 4 lines. 1, 2, 3, 4. And again, between 2 and 3, 1, 2, 3, 4. Okay, so each line represents 0.25 years or 1/4 of a year, which means that every 4 lines is 1 whole year. You'll notice on my dependent variable moving up from 0 right down here, you can go up 1, 2, 3, 4 to the 5th line. That means that each individual line represents a year. So 5, 6, 7, 8, 9, there's 10. Okay, so let's go ahead and plot our data. So the first data point that we had in our data table was the data point 0, 9. That means that at time 0, which is represented on our graph right here, the tree was 9 feet tall. So I'm going to go up here to 9. Here's 10. Right below 10 is the value 9. So our first data point is right there at 0, 9. I went over 0 and I went up 9. Our second data point is 1, 12. Okay, so 1 year after the tree was planted, it's now 12 feet tall. So I'm going to come over to my 1. I'm going to go up to 10, 11, 12. And I'm going to make my data point right there. So you can see now we have 2 data points on there. Our next data point was 2:14. So at the 2-year mark, I'm going to come right up here on this line, and I'm going to put a dot at 14 feet. 4:19 is our next data point, so I'm going to skip 3. Now it's okay to skip 3. There was no data point at 3. Perhaps this homeowner forgot to check the height of the tree. But we're going to move right over to the data point that we do have, which is 4:19. So I'm going to come all the way over to my 4, and I'm going to come all the way up here to 19, and I'm going to put another data point right there. So we have 4 data points. We do have 1 more data point to put on here, 5:20. So I'm going to come over to 5, and I'm going to move on up to 20 feet. So there are my 5 data points. So I've plotted my data points. I have my time values along my x-axis because that's my independent variable, and I have my height values up the y-axis because height is my dependent variable. So the next thing I need to do is I now need to go ahead and take a look at the trend and see if we can start to find that relationship that we were looking for. Okay, so I'm going to look at this, and just by looking at this, with the naked eye, I can see that these points look pretty much linear. I could pretty much connect these with a straight line, or pretty close to a straight line. So I'm going to go ahead and try to do that. I'm going to fit a straight line. Now these points will not all fall exactly on a line, but I can fit a straight line, which I'm going to put in a sort of turquoise color here. I can fit a line to this that is straight, that will be very close to all of my points. I'm not going to leave any points out. Some points could be on the line, some points might not be, but I'm going to try to fit a nice line to this that's nice and straight. Okay, it's going to look something like this. Okay. That line seems to go through a couple points, and it keeps all the other points that it doesn't actually touch pretty close to the line. So this is what's called a best fit line. Okay? This is the line that fits the data the best. And we're going to use this best fit line and its actual linear equation to help us find a relationship between the time that we allow the tree to grow for and its height. Okay, so I want to move on and try to do that now. So come over here, and we're going to, again, like I said, we're going to start to look for the linear equation of our best fit line. And our linear equation of our best fit line is going to give us an idea of what the relationship is between our two variables. And when you have data, that's what you're trying to do. You're trying to find that relationship so that you can make predictions about what's going to happen. So your standard math class version of a linear equation looks like y equals mx plus b. The linear equation y equals mx plus b, you can see, gives you a relationship between what's on your y-axis and what's on your x-axis. And there are two other values that are important. The m stands for the slope of the line, and the b stands for the y-intercept. Now, these are values that we can determine looking at our graph, and that's the reason why this particular form of a linear equation is called slope-intercept form. It is based on the slope and the y-intercept. Slope-intercept form. So y equals mx plus b. I want to go ahead and try to figure out what m and b are so that I can rewrite this equation in a way that makes sense for me to understand what's happening with my data. So let's go ahead and try to do that. Alright, y equals mx plus b. Before we do that, let's actually talk about what we can replace y and x with. If I'm going to make sense of the data, I want to know what are the variables that I'm talking about. I don't have a y and an x. Instead of y, let's go back. Instead of y, I have height. So instead of using when I write my relationship, instead of using the letter y, I'm going to use something else, something that makes sense. I'm going to use the letter h. H for height, since that's what's on my y-axis. If I go back again, I see that time is the variable on my x-axis. So I'm going to choose to use something like the letter t in my equation to represent x. Now, m is a number. I'm going to try to determine what that number is, and b is another number, and I'm going to try to determine what that number is. I want to start with the b, because the y-intercept, I think, is a little bit easier to come across, and there's less to do than with the slope. Okay, so let's start with the y-intercept. This number, the y-intercept. Let's think about what that means. Y-intercept. To intercept something is to connect with it, to cut it off, to meet at some point. So we're going to go back to my graph, and we're going to look for the point that we would consider the y-intercept. Now, the y-intercept would probably be the point where my best fit line, this here, intercepts or meets the y-axis. Okay, so that point is located right there. Now, at what value does the best fit line and the y-intercept touch each other? The y-axis touch each other? They touch each other at the value 9. You can see that data point right there was the value 0, 9. 9 is the y value. So the y-intercept is located at the y value when x is equal to 0. So in this case, the y-intercept is equal to the value 9. So we can come back over to our equation, and we can replace the y-intercept here with the number 9. So right now we are looking like we're going to have a relationship that says h, the height, is equal to some number times however long we allow the tree to grow for, plus 9. Because the y-intercept in this case has a specific meaning, the y-intercept in this case specifically is considered to be h0, where 0 kind of stands for initial. The initial time. The initial time was 0. When the tree was planted, its height was 0. And this is going to go and allow us to transition from our specific equation for this data to a more general equation, which is something that we are going to want to use in the future. So let's go ahead and talk about the slope. How do we determine what this number right here is, the slope? Well, the slope, as you can see in the equation above, is given the value, the letter m as its variable, and slope is equal to, in math class, if you're able to count boxes, rise over run. Okay, we are going to talk about it as y2 minus y1. Now, y2 and y1 are parts of points divided by x2 minus x1. You can see that these two values have the same letter with them, and these two letters have the same value with them. So what we're going to be looking for are 2 points. One point, x1, y1, and the other point, x2, y2. And we're going to plug those 2 points into this equation to allow us to find the slope. So we're going to need to go back to our graph again, and we're going to need to find 2 points that are on our best fit line. So what I mean by that is that we only want to use points that actually touch our best fit line. So while this right here is a data point, it is not a data point that our best fit line goes through, which means the data point 1, 12 is not a point that we want to use. On the other hand, this data point right here and this data point right here both happen to be right on our line. So we're going to use these, and I'm going to call these guys point 1 and point 2. And we're going to figure out what their x and y values are so that we can put them into our slope equation. So let's see here. We want to create the coordinate point system here. Right here we want to put the x coordinate 4.1, and right here we're going to put the y coordinate 4.1. So if we go ahead and we look at what this data point is over to an x value or a time value of 2 and up to a y value of 14. Okay, so point 1, right, is 2, 14. And point 2, same idea, we're going to create our point, is going to be x2, y2. Now, you should notice that x2, y2 and x1, y1 are the exact variables that show up in our slope equation. So we're going to go ahead and we're going to finish this out and find out what this point is, and then we're going to transfer those values into our equation. So point 2 is 4, 19. So we're going to go ahead and put 4 here as our x2 and 19 as our y2. Now, these 2 points, 2, 14 and 4, 19, are going to be transferred into our slope equation. Okay, so let's come over here and let's jot those down. What we just decided on our graph is that 2, 14 was made up of x1 and y1, and 4, comma 19 was made up of x2 and y2. So we're going to go ahead and put those in the right spots. So I'm going to set this up. The first number we want right here is y2. Now y2 is listed over here as 19 minus y1. y1 is 14. On the bottom we want x2 first, that would be the number 4, minus x1 next is the number 2. 19 minus 14 is 5, and 4 minus 2 is 2. 5 over 2. Now, depending on if you're in a math class or a science class, and depending on the teacher, you're either going to leave this as a fraction, 5 over 2, or you might convert this to a decimal. My personal preference is that we convert this to a decimal, and so I'm going to go ahead and I'm going to list the number value for my slope right here as the value 2.5. Now, 2.5. What does that mean? What does a slope of 2.5 mean? So if we come over here, we can talk about a slope of 2.5. Now 2.5 what? Okay, I'm going to take this 2.5, and since 5 over 2 was a fraction, I'm going to write 5 over 2 actually as 2.5 over 1. And now I need to ask myself, well, what does that mean? 2.5 over 1. Well, 2.5 was the difference between two y values, each of which has a unit of feet. So that means this is 2.5 feet over the 1 is the difference between two different times, and those times each had units of year. So we're looking at a slope of 2.5 feet per year. So the units here are very important. We're always going to look at the units to help us figure out what this actually means. Now, 2.5 feet per year. I think I just figured out what's called the growth rate of this tree. So I could kind of write this as, for every year that goes by, for every 1 year, the tree should grow 2.5 feet. That's what the slope actually tells us. And the fact that this thing has a value that sounds like that, for every year the tree will grow 2.5 feet, allows us to determine what this value actually is. And again, that's going to go a long way for us in our general equation. So if we come back and we look at our specification for this data, we get it height is equal to 2.5 times the time plus 9. Now, what can we use that? So let's come over here, and we found the equation h equals 2.5 t plus 9. Now, we can use this equation to help us determine approximately how tall the tree will be, its height, at any time that we desire. So we could actually choose a value of t and say, in 10 years, how tall will this tree be? Well, let's find out. So let's try it. H equals 2.5, and for the t, I'm going to plug in the number 10, and then I need to add 9. Okay, so this says that at a growth rate of 2.5 feet per year for 10 years, I will be at 25 feet, plus the original 9 that the tree was when we planted it, says that the height of the tree will be 34 feet tall after 10 years. 10 years. Now, this is important because we just made a prediction based on our data of how tall the tree will be 10 years after it was planted. So that in and of itself is important for our specific data. It allows us to get some information and make a prediction moving forward about what is going to happen with this tree. The other thing it allows us to do, and that the units help us do, it helps us make a more general equation. H equals 2.5t plus 9 is our specific equation for this data. But if we want to know about the height, and we know that this is time, what is 2.5? 2.5 we said was the growth rate. So maybe I want to call that capital G, and that stands for growth rate. I can then write a general equation, height equals growth rate times time, plus, we already discussed what the general meaning of the 9 is. The 9 was that initial height, plus h0. Initial height. In this case, height at planting. So we can take this general equation, and this general equation we might be able to then apply to other plants or other people or animals or any other thing that grows, right? Now that we know the growth rate and we understand the data that we're looking at, we can use this general equation to move forward. And that's something that we're going to do regularly. So all of these skills, from calculating the slope to determining the linear equation of a set of data points to just simply graphing the data points, are important skills for us moving forward to help us interpret data and create meaning for the physical world around us.